acquired two web cameras, so which requires calibration by the user. This is quite cumbersome and quite difficult to do, which would not be suitable for education environment. The detection based on color blobs is not reliable and can be ruined by similar background colors, and also requires the user to manually select the joints when you start. So the best accuracy with object detection is using convolutional neural networks, which learn from training images. They run on the GPUs because they have good parallelism. A popular model is YOLO v4, and in our project, we've used YOLO v5 because that's an improvement of YOLO v4 and still very, very accurate. Unfortunately, it does require lots of training data. So our contributions, this is a system overview. So this would be a hypothetical child. This would be the chatbot interface, which directly works with Google Cloud. It is then used to control send information to the robot arm control, so it knows which object to point at. The robot arm control then uses data from the object recognition, which is using an Intel RealSense camera, to determine where that object is, and then control the robot arm to point at it. Just a brief overview of how the Google Cloud system works. You get speech to text, which then uses natural language processing. It then uses sentiment extraction to detect the intent, and then it passes it on to robot arm control. This will then send a reply using text generation and then text to speech to let the user know that it has received the voice or text command correctly. This is just a little overview of our chatbot user interface. As you can see, it's very user-friendly. We've got a transcript here in this text display. We've got a text box for input, and you can press the send button here. And we've got a microphone here, which you can hold down to speak to the chatbot and send commands. We've also got a simplified networking setup, which requires very little knowledge. It uses the modern Flask HTTP library, and it can communicate over our local area network using different Wi-Fi access point names. So it's very easy to set up for future research in the University of Auckland.
Hi, I'm Edmund Liu, and I designed the vision control system. Once again, the chatbot passes the intent to the vision control system. The vision control system also takes in an RGB in-depth image from the Intel RealSense depth camera, and it sends the commands to the soft arm via Wi-Fi. So the vision control system has 3 stages. The first stage is alignment of the RGB in-depth images. The second stage is a calculation or prediction of where the soft arm is and the rotation of the soft arm for YOLO v5 and Reasoner 18. And the third stage is calculating the command to send to the soft arm. To create the dataset to train YOLO v5 and Reasoner 18, I created an auto-augmentation tool. This tool takes in about 100 or so images per class with the background manually removed. Then it randomly pastes the object onto random backgrounds and adds other augmentations such as rotation, position, size, hue, noise, brightness. We found this to greatly increase the robustness of our model without having to manually label huge datasets. I did a brief ablation study on a small subset of our dataset, and I found that there was about 0.3 improvement in precision compared to no background replacement. I estimate this saved us about 440 hours of data labeling. Our final dataset comprised of 5,000 toy bear images, 10,000 soft arm images, and 10,000 human images straight from the COCO dataset. Now I'll talk about YOLO v5. YOLO v5 is a convolutional neural network, which both predicts where objects are as well as what they are. But it requires a very large data set to be quite accurate, which we have. It achieves state-of-the-art speed and very, very high accuracy. It's only a little bit lower than some of the best models, which are much, much slower. And it's quite robust to lighting and perspective changes. And we trained it to detect the soft arm, its joints, toy bears, and humans. Training took 48 hours or 20 epochs on an RTX 3080, and we achieved fairly high recall and precision of 95% on our test set. Overall, we found the YOLO v5 model to work very well. It ran at 20 FPS on a GTX 1650 mobile GPU, and we found it to be highly robust to changes in lighting in different backgrounds. This is actually quite notable because the soft arm is partially transparent and quite reflective, so the lighting and background affects the appearance dramatically. We also found that it could handle partial occlusions, such as by the plastic inflation tubes. Now I'll talk about Reasoner 18. the other neural network. So initially, we tried to use geometric calculations to find the rotation of the entire soft arm or the base rotation. We found this to be highly inaccurate due to the highly deformable nature of the soft arm. So instead, we looked at a solid bottom segment, the green, black, and red and blues section. Feeding that crop into a Reasoner 18 neural network, convolutional neural network, we predict just the rotation of the soft arm's base. And once again, we used our data augmentation tool. However, we found the accuracy to not be great, which was plus minus 8 degrees. And this is likely due to a few factors, such as the camera being placed slightly off from where it was trained, distortion in the camera lens, and just the network not being perfect. I think this could probably be improved in the future by trying to detect the whole soft arm rather than just the bottom segment. Now I'll talk about the vision control, which takes in the position and rotations of the soft arm from the previous convolutional neural networks. Soft arm control is very simple. It simply uses proportional control to calculate the angle of the target object and the angle of the arm. It finds the difference, and based on that, it sends a command of 1 or -1, or if it's already pointing at it, 0. This is because the soft arm air pumps can only be turned on and off. There's no fine grain control anyway. So this is quite a simple system. Overall, we found a system to be functional, but with 1 or 2 caveats. The first being that the base rotation accuracy prediction is mediocre or poor at plus minus 8 degrees due to Reasoner 18. However, joint rotation is quite high. Accuracy is quite high at plus minus 2 degrees. We found it to be very reliable and never failed to track the soft arm. However, it also ran at only 9 FPS, which was marginally acceptable for real-time control, but it can be optimized in the future. We're going to show you a demo video, but due to the lockdowns, some of the air leaks were not fully repaired and only some of the air sacs are fully inflated.
So, for example, we can just say hello using text. And if you couldn't hear that, using Google's text-to-speech, you can also hear the response. Other option is to actually use the microphone. Point at the human. So we can also use voice. So yeah, it's quite simple to use. And yeah, the rest of the project will be explained by my partner, Edmund Leal.
It doesn't do the rotation properly, but it's right, but it's going up and down. In conclusion, we created a integrated chatbot and soft arm control system which is suitable for education, which is easy to set up. However, we also created a data augmentation tool which could be highly useful in other machine learning uses. In future, we could add more classes to our convolutional neural networks so they can detect more classes, and we could also fix all the leaks and physical damage to the soft arm. Thank you.
Hello everyone, this is the University of Auckland Engineering Project Group, Motion Similarity Analysis and Medicine Taking Action with Assisted Robots. I'm Ninga and my groupmate is Sahana. My supervisor is Hosak-an, and today I'm going to talk about our project and my contribution. In the current society, the elderly make up the majority of long-term patients who require medical attention. According to the New Zealand Doctor Workforce Survey in 2018, there are only about 333 doctors for every 100,000 persons in New Zealand, and COVID-19 puts these prospects much more at risk, and robots become a handy companion in this scenario. In the University of Auckland Cares Department, also called a Center for Automatic Robotics Engineering Science, we have healthbots such as Charlie and iRobbie, which are robots that specialize in healthcare systems. They monitor the health status of patients, provide medical assistance, and detect possible faults. However, the current functionality is limited, not enough for them to be full-time healthcare assistants. In this project, we want to extend the functionality of CARE's healthbots and improve their current supervision abilities to especially support patients with COPD and dementia. One of the main supervision components of the system is medicine consumption. As helping them to take their medication, we want to analyze possible solutions and recommend the one that reaches at least 80% accuracy in near real time. And this is my project goal. I want to create a system that recognizes medicine-taking movements during patients' daily medication routine. And their assumptions and limitations under our system remains consistent. Movement can only be detected in the range of camera vision. For medicine consumption recognition part, there are only 2 variations of medication pulses capture, and the software system runs with Python 3.8 and TensorFlow tools. For the literature review, we gathered papers that implemented the motion recognition and found some key topics to focus on: human pulse estimation, feature extraction, and recurrent neural networks. I realized that there were 2 ways to create a functional system. One of them was with a feature extractor and RNN. The chosen model for the feature extraction is VGG16. The reason for choosing VGG16 is based on its performance on ImageNet. Its accuracy can reach to 92.7% for its top 5 accuracy, which is easier to implement. Then in Slowfast, which is also a useful model with 79% accuracy on Kinetic 400 dataset. Then based on the paper performance and CPU running environment, I chose to use VGG16 in the medical action system. So I've been searching through the datasets to find a suitable one, but most of the datasets contain quite a lot of movement, but there is no datasets that includes taking medicine movement. Then I decided to build my own dataset. In the medicine taking action dataset, which is built with 2 motions, as you can see from the slides, taking medicine and drinking water. Each class has 10 ABI videos, and it will be pre-processed into 140 frames of each video and resized into 2:4x2:4 to fit the VGG16 model input size. And here is a system diagram and the methodology. The main topic for this system is action recognition. As mentioned, the videos will be cut into frames, and the test videos will be analyzed and extracted the features with a pre-chained VGG16 model as a feature extractor. After fine-tuning or unfreezing its top 4 layers, the seasoning with RNN models, and with the RNN model, an LSTM model is used to classify the movement belongs to taking medicine class or drinking class, with the analysis of accuracy and probability as the motion recognition as shown in the system diagram. And here is the training and testing result. We can see from the graph, the training accuracy is quite high. The accuracy starts from 62.7%, and the highest accuracy before overfitting can reach to 99.6 for both VGG and 60 and IN in the first 10 epochs. And it will overfit after 10 epochs, which means good performance on the training data, but poor generalization to other data. Then during testing the models with test videos, the accuracy of drinking water action can reach to 66.5%, while 53.8% with medicine action. The outcomes of the research were that I was able to implement an independent software system that recognizes medicine actions, along with the accuracy at which the system predicts this action. It can be integrated with the UOA Cares healthbots or outsourced to work with other hardware. Scalability was also tested and confirmed for the system, allowing the more actions to be added at a later stage. The impacts of our research are that we were able to support elderly patients and their desire for independency by allowing supervised medicine consumption. We ensure that their safety is of the highest priority. We believe that such a system would be able to satiate demands and physiotherapists and doctors in New Zealand. To summarize, we were able to achieve our project goals and create a recognition system for medicine. Our observation were that the functionality of system depends on whether or not it has the GPU. The feature extractor with RNN was incompatible for real-time detection on CPU, but a good performance on the GPU support laptop. For the future work, depth was something we wanted to use during testing, as not much state-of-art information or procedures exist for depth imaging. However, another important prospect would be sending alerts to doctors when patients are exerting. Strain can be detected using media pipes, face landmarks while exercising, and using robot gen directly to contact their registered doctor. And that's it. Thank you. So this is our demo video, testing with drinking water and taking medicine pose. So the prediction result will be shown on the top left corner of this test window. This is drinking with straw, and this is drinking with mug. And I also test with turning with different angle. This is taking medicine with palm. The result will be also shown on the top left corner as well.
Hi, my name is Ahad, and I've been working alongside my partners Iiccc and Hoseok on the development of a cost-efficient soccer robot via 3D printing for a robot soccer system. What is robot soccer? Robot soccer is a simulation of a game of football between two teams of robots. Robot soccer is a gateway into STEM for younger people, as it teaches them things about robotics, coding, and many more. The current design of the robot soccer robot uses some type of control loop to make sure the robot moves accurately. It uses some type of Zigbee communication protocol to communicate between the PC and the robot itself. And the main body of the robot is machined using some type of aluminum or iron or stainless steel. This design costs approximately $1,000 and is no longer being manufactured. So this brings us to our proposal. We would like to design a new cost-efficient design of the robot body as well as the PCB. We would like to identify and implement the most ideal control system for DC motors, and we'd also like to identify and implement the most ideal communication protocol for robot soccer system. In terms of what is most ideal for communication in robot soccer, it is a communication protocol that has low latency and can have a decent range, because robot soccer is a very fast-paced game. In terms of the control system, we need a control loop that will make sure that our robots move to the exact position. Because of the vision system, we know that there will be inaccuracies, so it is important to have a very accurate control system. How did we divide the task?